Well, good evening and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here. It's great to see a number of familiar faces. We've also got some relatively fresh faces. Who's maybe here for the first time or hasn't been here since 4th grade? All right, very good. Great to see you. I know we've got a number of members. You want to just raise your hand if you're members, right? Basically the other half. Kopernik is, we're a nonprofit. We're an informal we're a public observatory informal science center, and we belong to what's called the ASTC, Association of Science and Technology Centers. And a Kopernik membership actually gives you a particularly valuable piece of paper in that with your Kopernik membership card, you can get into over 350 other science centers. So if you like this kind of place, a Kopernik membership is pretty inexpensive, and you can go to the Robeson Museum and Science Center, you can go to the Ithaca Science Center, you can go to the Intrepid down in New York City, or the Franklin Institute in Philly, and 346 others, as it were. So if you like this kind of place, you want to consider getting a getting a membership. Kopernik is really all about trying to sort of making people aware of how the world works. We really try to promote lifelong learning. We start as young as 3 years old. We have a program called Kopernik Kids that we do usually about once a month. But on Friday nights, we do this kind of program. We do an opportunity to learn, again, how the world works. Not everything we do is always about astronomy, although tonight's program actually happens to be astronomy. Next week, we actually have a presentation called TikTok, but it's T-A-C-K-T-A-L-K. And so actually it's an outreach person from the Central New York Lyme Alliance talking about Lyme disease and sort of, how it's really been getting worse these days and how to protect yourself. The following week, we'll have a program on concussive brain injury, what happens to the brain, like with football injuries and that kind of stuff. The weekend after that, we actually have a meteorologist from the National Weather Service in Binghamton. We'll talk about sort of how El Nino is going to affect us this winter and sort of a long-range winter forecast. And then we always do black holes on Black Friday. And so we've got a number of great talks lined up, and so you're welcome to come up here for that. One of the things we do here is, let me just actually get out of this right here. And so back in 2020, we had a number of speakers lined up, and let me just get let's go and do this right, Drew. And where did I go? I didn't actually just see what we can do. So we created, we have a YouTube channel. We said, let's actually get those people to zoom in to us and turn it back around. So if you go to our YouTube channel, and there are a number of people watching on the YouTube channel this evening, here's our program to Bennu and back. Last week we did a talk on the International Observe the Moon. And there are, so even if you miss our program, look at it on the YouTube channel. What's nice about this is we now have over 13,000 subscribers, and it has actually allowed us to do outreach literally around the world. But anyway, we're going to focus now on tonight's program. We're very fortunate in that to have access, relatively access to a scientist working on the OSIRIS-REx mission. If you recall, and I'm sure Dathon will tell you about it. It literally just returned to space from space just a few weeks ago, and in fact, exactly a month ago. And so I'm going to stop talking and let Dr. Dathon Golish, who's an imaging scientist at the University of Arizona, take it from here. So, Dr. Golish, thank you for joining us tonight.
Thank you for having me. Thank you for the introduction, Drew. All right. let's get started. So hi, everyone. My name is Dathon Golish. I am a scientist at the Lunar and Planetary Laboratory at the University of Arizona. And we are here tonight to talk about OSIRIS-REx and its journey to Bennu and back and beyond. Now, I want to say up front, I know the folks that listen in on these sort of talks are pretty avid consumers of science information and science news. So I wouldn't be surprised if a lot of you are pretty familiar with OSIRIS-REx. In fact, I wouldn't be surprised if a couple of you know things about OSIRIS-REx and Bennu that I don't know, which is great. But I know also probably there are folks listening who have maybe not heard as much about OSIRIS-REx. So I do want to start a little bit general. I want to talk about Bennu and why it's interesting, OSIRIS-REx and what sort of instrumentation it brings to studying an object like Bennu, before we move along into the really exciting stuff, the sample collection, the sample return, and then what's happened since then. So let's start with Bennu itself. Bennu is a near-Earth asteroid, meaning it has an orbit similar to the Earth. You can see there it has an orbital period of 1.2 years, that's Earth years, very similar to the Earth. Its orbit is a little bit inclined with respect to the Earth, so whereas the Earth is at sort of 0 degrees, Bennu's orbit is tilted up just a little bit at 6 degrees. Bennu is about a half a kilometer in diameter. That's a couple city blocks, so pretty big. And it's got a very reasonable rotation period of about 4 hours. That's a Bennu day. It's 4.3 hours long. This view you're seeing on the right is a Bennu day. This video you're seeing is not directly spacecraft data, but it is generated from spacecraft data. So the visualization wizards at NASA take a couple products from us on the mission. First, they take a high-resolution shape model, or a 3D model of Bennu, of the asteroid. They take that into their software and they layer on top of that images that we also acquired of Bennu. That tells us, you know, that rock is dark, that rock is light, etc. And then they add this cool illumination variation so that they can simulate what it looks like to see a day pass on Bennu, with the sun rising in the east and setting in the west. And you can see, even from this video, that Bennu is a dynamic, varied, interesting surface. It's rocky and cratered, and it has stuff everywhere you look. And it's a fascinating place to go as a planetary scientist, and a challenging place to observe as an imaging scientist. But a lot of folks ask, why Bennu? Especially, you know, before we ever got to Bennu and we didn't know it looked like this, what made us choose Bennu out of the literal millions of asteroids in the solar system? And it's a good question. This video, which hopefully is coming through okay on Zoom, this video is a record of the discovery of asteroids in our solar system. So if you look in the bottom left-hand corner, hopefully you can see my mouse down here. That's the time, the year that the data was being acquired. And the number next to it is the number of asteroids we currently know about in the solar system at that time, in that year. And then if you look at the movie part, we've got the sun in the middle in yellow, we've got planets whizzing around it in blue, and everything else you see here is an asteroid. The green ones are out in the asteroid belt. The red and yellow ones are ones that cross into the inner solar system, either coming through Earth's orbit or through Venus's orbit. And the white flashes that you're seeing, those are asteroids as they're being discovered at that time. So right now in the video in 1989, those are the...
We probably lost about the last minute, I'd say.
Okay. I can start this slide over if that makes sense.
Sure, please, thank you.
Sure. All right, let's try this again. Okay, so forgive me if I'm repeating anything, but I'll start here again. So this is a video of asteroids as they were discovered in our solar system. In the lower left of this video, you can see a year, 1982, at this moment. The number next to it is the number of asteroids that we currently know about at that time, at that year. In the video, you can see there's a yellow blob in the middle, that's the sun. The sort of cyan blobs that are going around it, those are planets, the third one being the Earth. And everything else you see is an asteroid. The green ones are out in the asteroid belt. The red and yellow ones are the ones that cross into the inner solar system. And then those white flashes you're seeing, those are the asteroids as they're being discovered at this time, currently 1988 in the video. There's a couple interesting things you'll see about that. First of all, those white flashes always happen away from the sun. They always happen when the part of the Earth that's doing the observing is during the night, so it's looking away from the sun. You'll also see that these flashes tend to come in waves. There are times when there's more of them and times when there's less, and that actually has to do with weather. So there's only so many of these all-sky surveys, these observatories that are set up to look for these asteroids. And depending on where they are in the world, their weather impacts when they're able to observe. So one of the big surveys is called the Catalina Sky Survey. It's here in Tucson, Arizona. And in the summer, the late summer, we get monsoons where there's a lot of storms and you can't do a lot of astronomy. So that part of the year, there's less of these white flashes. And in other parts, there's more. So we're here in 1997. When this video started in 1980, we had less than 10,000 known asteroids. Now in 1998, we're just crossing 50,000. If I jump to the end of this video, which is only in 2011, you suddenly see a lot more. Now we know in 2012 here, more than 500,000, more than 500,000 known asteroids. So how in the world do we go from that? This is sort of the time period when we were choosing our asteroid, Bennu. How in the world do we go from that overwhelming abundance of options to Bennu? This little graphic kind of shows that. So, oops, I guess I lost my video at some point too. Let's start that again. Okay, great. So this little graphic shows how we came to choose Bennu. First, at the very bottom, we have over 500,000 asteroids, the ones we started with in that video. Immediately, we can knock that down to just around 7,000 by selecting near-Earth asteroids. We don't want to go out into the asteroid belt. We also don't want to get too close to the sun because our spacecraft would get hot, and actually our sample would get hot too. So that knocks us down to about 7,000. Then we can knock that down further by considering asteroids that have orbits that are good for sample return, not just for us to get there, but for us to get back home afterward. That brings us down to under 200. Then we can consider the size of the asteroid. This is another sort of Goldilocks thing. We don't want to be too large. That makes sampling a little bit more challenging, but fortunately most of the near-Earth asteroids aren't that big. But we also don't want it to be too small. We need an asteroid that's at least 200 meters in diameter because we need it to have some gravity. We want to be in orbit around this asteroid. There's not a lot of gravity, but just enough that we can stay in orbit so our spacecraft can stay in the vicinity of the asteroid for a couple of years while we study it. So that brings us down to just 26. Then the scientists got involved and said, okay, well, what we really want not only to observe, but to bring a sample back from is a carbon-rich asteroid, carbonaceous asteroid. At this point in time, when Bennu was being selected, we had only sampled from one of these small bodies, an asteroid called Itokawa. And that Itokawa was called an S-type asteroid. It's very different from Bennu. And so the scientists said, what we would love to see is something that's rich in carbon, because that's not only a different thing than we've already seen, but that is a window directly into the early solar system and how the building blocks of our planet and even maybe life on our planet might have been transported around that solar system. So that brings us down to 5 very good candidates, and from that we selected Bennu. Of course, Bennu wasn't called Bennu when we first selected it. It was called 1999 RQ36, indicating when and how it was discovered. So we needed to get it a name. And how we did that is holding a contest. We opened up to the world to make suggestions for what we should call this 1999 RQ36 thing that we wanted to go visit. And the winner of the contest was a 9-year-old kid named Michael in North Carolina. He submitted the idea of Bennu. He had been doing some research and found this mythological bird in Egyptian mythology called Bennu, and connecting that to the Osiris name, the sort of Egyptian vibe, he suggested Bennu, and that was the one that was selected, and that's what it was called forevermore. The other little cool piece of that I actually only learned about a month ago, I saw a news article. Michael, the 9-year-old who chose Bennu's name, is now a 19-year-old and in college and is actually pursuing space science. He's in college and he wants to be an astronaut. So it's kind of neat that the person who named Bennu is maybe going to end up in planetary science himself. So, okay, so now we have our target, Bennu, and we know a little bit about why it's interesting, but what do we want to study about Bennu? And that really brings us to OSIRIS-REx's name. OSIRIS-REx is one of these long acronyms, but the name actually does a pretty good job of telling you what OREX is all about. OSIRIS-REx stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer. And if we step through that one by one, it kind of maps out what we want to do at Bennu, or what we did at Bennu. We start both literally and metaphorically with origins. Bennu is what we call a primitive asteroid, meaning it hasn't changed much for billions of years. Bennu was presumably part of a larger parent body once upon a time, probably out in the asteroid belt, and some impact removed some material from that parent body. And that material sort of floated off on its own and coalesced into Bennu, which eventually migrated into the inner solar system. Since then, Bennu hasn't really changed a lot. It experiences illumination from the sun. It gets, micrometeorite impacts, but that's about it. There's no weather. There's no, tectonic activity. There's not a lot that's changing Bennu's composition, which means by studying Bennu, we really have this window into the early solar system, which is cool not only because we get to understand what Bennu was like billions of years ago, but also because that's the starting point for a lot of the subsequent evolution that happens in the solar system, how that solar system changes, how our planet forms, and potentially even how the building blocks of life are transported around that solar system and may be brought to Earth. How we're going to do that studying is the spectral interpretation part. We looked at Bennu with a suite of instruments, which we'll talk about in just a moment. And the spectral part is really saying we're looking at Bennu in multiple colors, a wide range of wavelengths, which is colors, from the visible light that we see all the way out into the infrared and in fact into the X-ray. Spectral interpretation is saying that we want to look at this surface, this Bennu surface, this asteroid surface, and all these different wavelengths to better understand what that surface is made of, what its composition is. And that kind of leads us to resource identification. Resource identification is, what is Bennu made of? There's this idea that we might, in the future, mine from asteroids, that we might extract valuable materials from them. Resource identification is, how can we map the chemistry and the mineralogy of this primitive asteroid and understand better how we might be able to get stuff out of them. Security is a big one. Bennu at the time, and in fact still, is one of the asteroids that's on our potentially hazardous list. There's a list that is maintained to keep an eye on all the stuff that's out there. Now, Bennu's not actually particularly dangerous. It's got like a 1 in 2,000 chance of hitting the Earth in 100 years or something. But still, it's on this list. And the reason we want to study it is so we can better make those predictions. How likely is it that something's going to run into the Earth? That is, of course, largely to do with gravity. That's controlling the orbit of the asteroid around the sun. But there are also other subtler effects that can have real impacts on that orbit. One of them is something we've listed here called the Yarkovsky effect. The Yarkovsky effect, I'm going to hold up my little Bennu here real quick. The Yarkovsky effect is when the sun shines on one side of Bennu, and then Bennu rotates through its day. That heat that picked up when the sun was on it is radiating off during the Bennu night. That radiation, the original illumination and then radiation, can actually change the orbit of Bennu. Not over days or years, but over decades and centuries, it can have an actual real measurable impact on Bennu's orbit. It can change how likely it is or isn't to hit us.
If it's okay, I'm going to pass along our Bennu.
Yes, absolutely.
I think this is pretty much the same 3D model that Dr. Golish has. So you can pass that along.
Great.
That's a 1/5000th model of Bennu.
Great, thanks, Drew. So by studying this effect and other effects on Bennu, it helps us predict Bennu better, but it also helps us predict other of these small objects better. Other objects that maybe we'll discover in a year or 10 years, and we want to be able to predict its path to know if it's a potential hazard to the Earth. understanding the Yarkovsky effect helps us better do that. And then finally, the star of the show, regolith explorer. The whole goal of the OSIRIS-REx mission is to sample the regolith, the rocks on the surface of Bennu, and bring them back to the Earth for future study. So we've got our target and why it's cool. We've got what we want to do there, but how are we going to do it? And that brings us to the spacecraft. This is a very cool top view of the spacecraft. We're looking down onto the science deck. So that's where most of OSIRIS-REx's science instruments are. You can see those sort of scattered around the top, and we'll go through those in more detail in just a second. But in the middle there, you can see that big white cone with the orange bottom. That is the sample return capsule. That is where the sample was stored after we collected it from the surface and kept safe for its 3 years until it was able to come back to the Earth. And just that white and orange part is the part that separated from the spacecraft and descended into the Utah desert just a month ago. You can see a couple other things in this image, the solar panels on the side, that big gray cone in front that's sort of pointing down and to the right in the picture. That's our high gain antenna. That's how we transmit most of our data back and forth to the spacecraft. There's a couple other antennas, a medium gain and 2 low gain antennas on there. That's for when we can't be positioned such that the high gain antenna is pointed at the Earth. The total spacecraft mass at launch was over 2,000 kilograms, but more than half of that was fuel, much of which we've used at this point to get to Bennu and back. But there is actually some left in the tank, and we'll get to that at the very end of the talk. But first, I want to go through a little bit more about these instruments, because they really are what produced all of the science we got out of Bennu, so they deserve a little bit of individual attention. First up is the OSIRIS-REx camera suite. This is the one that I worked on, so of course it's my favorite. This is how I joined OSIRIS-REx 10 years ago, almost exactly 10 years ago is when I joined OREX, and it was to work on these 3 cameras. OCAMS is really 3 instruments. The first is Polycam in the upper right. That's our telescope. That was the first OSIRIS-REx instrument to acquire Bennu from far away, but it also did high-resolution mapping of the surface. MapCam on the left is our color camera. Not quite as high resolution as Polycam, but it takes images in color. So we're able to make color images of the surface, but it also produces a lot, maybe the majority of the imaging science from the surface of Bennu. And then SamCam at the bottom, that's the baby of the family. SamCam's whole purpose in life was to document a sampling event. All 3 of these cameras were designed, built, and tested at the University of Arizona where I work. Next, we have a suite of spectrometers. Remember, a lot of what we want to do at Bennu is the spectral interpretation, and these 3 instruments contribute to that. The first is OSIRIS, our visible and infrared spectrometer. So this isn't a camera like we were just looking at with OCAMS. It doesn't take a picture. It just looks at one spot at a time. But at that spot, it looks at this wide range of wavelengths or colors. It starts all the way down at 0.4 microns, which is basically the blue you see with your eyes, and goes all the way out to 4.3 microns, which is well into the near-infrared part of the spectrum. OSIRIS was built at NASA's Goddard Space Flight Center, and it is part of that spectral interpretation story. We can use the spectra, the response of the surface to the different colors of light illuminated by the sun, how much of those different colors reflect back off of that surface and are detected by OSIRIS tells us what that surface is made of. If we look at the surface and we see it's reflecting more of this light than that light, and then we look at our library of all the known minerals and materials, different compositions, we can say, well, this looks an awful lot like this thing in our library, therefore we know that Bennu's surface has some of that on it. OSIRIS pairs very naturally with the second of our spectrometers called OTES. This is our thermal emission spectrometer, built at Arizona State University, just about 100 miles from here. OTES is another spot spectrometer. It's looking at one spot, but again with this wide range of wavelengths. OTES picks up basically where OSIRIS left off at 5 microns, already into the infrared, and goes all the way out to 100 microns, far into the thermal infrared. OTES looks at thermal information. If you've ever seen one of those thermal cameras, like at a science center, where you can sort of see your heat, or like night vision goggles, that's kind of what OTES is doing, not as an image, but as a spectrometer. It's looking at Bennu and it's also producing spectra that can tell it stuff about what the composition of the surface is. But it's also translating those directly into temperatures. It can say, as Bennu orbits throughout its day and sees Bennu's sun-facing side heating up, and then as it rotates into the night, it sees that side cooling down. It can track those temperatures, which is cool by itself, but then they can also say something about the composition of the surface, because it turns out that dense rocks absorb and release heat differently than really porous rocks. So by sort of reversing that, they can figure out what the composition of that surface is. And then third in our spectrometer suite is REXIS. It's the Regolith X-ray Imaging Spectrometer. REXIS is actually a student instrument. It was designed and built and operated by students at MIT. It's another spectrometer, but this time looking at X-rays. When the sun shines on the surface of Bennu, some of those elements fluoresce and release light in the X-ray wavelengths. REXIS is able to detect those and then tell us what those elemental abundances are on the surface of Bennu. And then finally, we have the OSIRIS-REx Laser Altimeter, or OLA. OLA was produced by the Canadian Space Agency, and OLA is a LiDAR, or a laser radar. The way OLA works is it fires a laser down to the surface of Bennu. That laser reflects off of the surface and bounces back toward OLA, which OLA detects. OLA is able to very accurately measure how long it took for the laser to travel at the speed of light to the surface and back. And from that, it can measure exactly how far away that surface is. Then it has a scanning mirror, so it sweeps this laser over the whole surface of Bennu, and then it kind of reverses that math, and instead of measuring, well, by measuring how far it is to the surface, it can imply the shape of Bennu. OLA is what produced that super high resolution shape model, or 3D model of Bennu that we saw at the very beginning in that visualization. In fact, OLA produced the highest resolution shape model that covers a complete planetary body that we've done. OLA measures, its shape model was accurate to something like 5 centimeters over the 500-meter diameter of Bennu. It's really impressive. Our science instruments are then paired with some operational instruments, although as it turned out, we use some of these for science too. We have 2 navigation cameras. These are used to navigate with respect to the stars and space on our way to Bennu, but they were also used to navigate with respect to Bennu itself. In fact, these cameras were used to guide the spacecraft as it descended to the surface during sampling. The computer on the spacecraft has a library of landmarks that we knew about after we did a bunch of imaging on the surface of Bennu. The spacecraft, during descent, completely without us being involved, this is totally autonomous, took pictures of the surface and compared what it saw to its library of landmarks to know that we were on track, that we were headed down to the right sampling spot. And it did that all the way down to make sure that the spacecraft was safe. We also have some redundant LiDARs, these laser radars on board. These were sort of a backup solution to the imaging solution I just described for sampling. The imaging solution worked so well that we didn't need them, so we didn't actually use them at Bennu, although we might use them in the future. And then finally, there's a special camera called StowCam. Its whole purpose was to document stowing the sample safely into the sample return capsule, that white cone that we just saw. Document that it went into there, that it was safe in there, and that it got sealed up. So this suite of instruments took, for me, 3 years to develop on the cameras, but for some people, nearly a decade, from proposal through building the spacecraft, through building all of these instruments. And all of that is culminating in September 8th, 2016, when Bennu launched off of the surface of the Earth. This was really the beginning, sorry, I said Bennu, when OSIRIS-REx launched off the surface of the Earth. This is really the beginning of OSIRIS-REx's journey to Bennu. I was here for this, and I can tell you, in a personal sense, there's something pretty cool about watching something that you helped build leave the Earth. I touched that spacecraft. I had gloves on, but still, I touched it. I held those cameras, and now I was watching them blast through the atmosphere and leave the Earth to begin their journey to Bennu. It was a pretty amazing experience, a pretty unique experience that I don't know if I'll get to have again.
Was OSIRIS-REx the only payload on that rocket?
It was, yep. It was just for us. So OSIRIS-REx's journey to Bennu took about 2 years, but about halfway through that, we swung back past the Earth. So you may remember I said just a second ago that Bennu's orbit is sort of inclined. And so to boost us up toward Bennu, we used Earth's gravity. We swung past the Earth and we used its gravity to sort of boost us in the direction of Bennu. But while we were doing that, we took data with all of our instruments. This was mostly a calibration exercise to confirm that the instruments were working in space like they work on the ground. But it was also an opportunity to take a pretty cool planetary selfie with our color camera, MapCam, looking back at the Earth, and also some pretty cool images of the moon with Polycam, our high-resolution camera. But a year later, it is time for us to approach Bennu. And I'll pause here and say for a second that at this time in 2017, 2018, as we're approaching Bennu, we as a global science community have only really been to and sampled from one of these small near-Earth asteroids. That asteroid is called Itokawa. It was visited, this is the one on the left, visited by the Japanese mission Hayabusa in 2005. Itokawa's a little bit smaller than Bennu. It looks like a sort of a space potato, and it's got smooth areas and rough areas. And before we really knew anything about Bennu, we thought we would find a smooth area on Bennu and sample from there. In 2018, on the right, about 6 months before we got to Bennu, the Japanese mission Hayabusa 2 got to their target asteroid, Yugu, which is the one you see on the right there. Looks an awful lot like Bennu, actually. And when we saw this, we thought we might be in a little bit of trouble. Yugu, in principle, had a lot more in common with Bennu. They're similar shapes from radar, similar spectral types, similar sort of solar system histories. And so when we saw this, we thought this might be a sneak preview of what we're going to see at Bennu. And we thought we might have our work cut out for us. And in fact, to emphasize that a little bit more, this image on the left is one of the simulations we made of Bennu before we ever got there, or before Hayabusa 2 got to Yugu. And the shape is about right, because the shape is from the radar shape model. But the details were a guess, because we didn't know yet. We put some rocks, and we put some craters, and we added some texture, but we didn't know what Bennu was going to look like until that sneak preview. And then, in late 2018, we saw the real thing and saw that it was quite different than our expectation. This is a challenging surface, a fascinating surface, but to go down and sample from it, we thought was going to be pretty tricky. But before we get there, I think it's worth appreciating this surface a little bit. Even from this zoomed out view, this sort of global view, you can see all kinds of interesting features. And I want to talk about just a couple of them. The first is a feature called Ben-Ben. Ben-Ben is the tallest thing on Bennu. It's like, I can't remember, 30 meters tall or something like that. It's so tall, in fact, that this is actually the one thing we knew about on Bennu before we got to Bennu. We could see this even in the radar shape models from Earth because it sort of protruded so much from the southern hemisphere there. So we kind of knew that was going to be there, but we didn't know what it was going to look like. Kind of interesting, actually. It kind of looks like the rest of Bennu. It sort of has a similar shade, a similar gray level. It's just really tall. In contrast, the second one we'll look at is called the Rock. The Rock is actually the biggest thing on Bennu. It's 100 meters across. It's not as tall as Ben-Ben. It doesn't stick out quite as much, but it's biggest in the sort of the longest dimension. But it's interesting not only because of that, but also because of what it looks like. It is exceptionally dark. It's made of this dark, rough material. It turns out, as we studied Bennu more, that it seems like Bennu is kind of made of two things, at least primarily. Lighter rocks, although all of Bennu is very dark, but relatively lighter rocks that tend to be a little more angular, a little bit more flat, and then these very dark rocks that are rough, sort of like we call it a cauliflower texture. And the rock is a prime example of that darker texture. So dark and so rough that you can see it even from the global view. Another example of that, much smaller, is a feature called the gargoyle. It's a little bit hard to see from this side view, that's the high resolution view, but when you look at it from above, it really does kind of look like a gargoyle perched on the surface. And it's made out of this dark material. and yet it has this little white rock you can see in the image on the left that sort of looks like it's just sitting on the gargoyle's left shoulder. All of that makes the gargoyle interesting by itself. It's also kind of cool because by complete coincidence, the gargoyle is sitting just outside of our backup sampling site. Not the one we ended up going to, but the one that we would have gone to if something didn't work about the first one. Our backup sampling site is called Osprey. It's a big crater on the equator, and the gargoyle is sitting just southeast of that site, almost as if it's sort of standing guard for us. And then the last one I'll show is called Simurgh. Hopefully I'm pronouncing that right. You may have noticed a theme here. All of the features on Bennu are named after mythical winged creatures because Bennu itself is a mythical winged creature. So Simurgh is interesting not only because it's one of these pretty big rocks on the surface, you can see it from orbit, but also because, by coincidence, it just happens to be at Bennu's prime meridian. We had, before we ever got there, defined approximately where the prime meridian of Bennu would be. And so when we got there, we looked for something that could be that marker. And Simurgh just happens to be straddling that prime meridian. So we used it, or rather a small rock that's just off of it, to define the 0 point in Bennu's coordinate system. We could spend literally this entire hour just zooming in on the surface of Bennu. There are so many fascinating things to see. But of course, we don't have time for that. So instead, I want to zoom out and show you the whole surface. This is the global base map for Bennu. This was sort of our reference for what Bennu looks like. And this is important, maybe one of the more important data products we produced all of our time at Bennu for a couple of reasons. One, it just gives us a good sort of, like I said, reference for what Bennu looks like. This is a mosaic made from hundreds of images, and all those images were acquired at like 3 p.m. on Bennu, 3 p.m. locally on Bennu. And that gives us these wonderful shadows. So you can see all of the texture on Bennu. You can see the craters, and you can see the mounds, and you can see the shadows off of the big rocks. You get a real sense for the texture on Bennu's surface, which also leads to some wonderful scientific conclusions. When we measure the craters and the crater population, that tells us about the meteorite impacts. When we measure the boulder population and how they might have moved around the surface over time, that tells us about Bennu's history. But on top of this cool science stuff, this was also sort of our home base for looking for a sampling site. This, combined with lots of other scientific data from Bennu, is what we poured over to find a safe place to sample on that surface. Somewhere that wasn't so rocky, that didn't have huge boulders, that had fine material that looked like we could scoop it up into our sampling device. This was the image that people spent literal hours just going over trying to find those spots. But then we combine that with a bunch of other spacecraft data. So this one is the global albedo map of Bennu. And if I blink back and forth kind of slowly between the two, you'll see that it has all these large features in common. But this one, this albedo map, also constructed from hundreds of images, these images were acquired at noon on Bennu. So the sun's right behind us when we're taking these pictures, which means there's not a lot of shadows on purpose. That means all of the variation you see in brightness isn't due to shadows, but is due to the inherent brightness of those objects. That rock isn't dark and that rock isn't light because one's in the shadow and one's in the sun. They're dark and light because that's truly what they look like, which led to that conclusion that there's these bright and dark rocks on Bennu. We can combine that further with a color map of Bennu. Again, I'll blink back and forth a couple times so you can see how all the features are in common. This is, of course, not what Bennu actually looks like in color. This is exaggerated to highlight the science we can pull out of this data. But you can see really interesting things, like the rock, for instance, in the lower left part of Bennu is red. It's redder on average than the rest of Bennu. That's true of a lot of dark things on Bennu. Dark craters and dark rocks tend to be redder for some reason. On the flip side, there are some rocks that appear to be bluer, that appear to be these sort of fresh-faced rocks that are bluer than the average Bennu, which is telling us something about the composition and the texture of those objects. And then we combine this with a ton of other information. We make photometric maps of the surface, spectral maps, thermal maps, altitude maps, geologic maps, all of them telling me things that I don't even know about the surface of Bennu, but told the dozens of scientists working on OSIRIS-REx, all kinds of stuff about the surface of Bennu. And then we're synthesizing all of that information to where is safe, where can we go, where is interesting, and what does it tell us about Bennu as a whole. And this is all the global work. As soon as we start zooming in on Bennu, we see spectra that tell us that the minerals on Bennu are hydrated, meaning they have water locked up inside their crystalline structures. We see large rocks, like a meter large, that are 5 times brighter than the rest of Bennu, not like anything else on Bennu, probably because they're exogenous, meaning they don't come from Bennu. They were either delivered via meteorites, or they were part of the original parent body that got collated, combined with Bennu when it separated. These things don't look like the rest of Bennu spectrally. In fact, they look the most like Vesta, one of the largest asteroids in the solar system out in the asteroid belt. We also see carbonate veins on Bennu. These are centimeters thick, a meter long veins in these otherwise sort of normal looking Bennu rocks, but that are filled with carbonate. That tells us something about the geologic history of Bennu. It implies that there might have been fluid flow once upon a time, probably way back on the parent body, that generated these veins. Some of this we expected, like the water, we expected to have hydrated minerals. Some of it was a surprise. And maybe the biggest surprise at Bennu was occasionally we would see stuff just flying off of the surface. Bennu, as it turns out, is what we call an active asteroid, meaning it sheds material, kind of like a comet, but for different reasons. We don't know for sure what those reasons are. It could be little meteorite impacts. It could be thermal fracturing. Whatever it is, occasionally, and not rarely, we saw this multiple times in our 2 years at Bennu, but occasionally rocks would just kind of explode into the air. Well, there's no air, but into space. Most of those rocks would descend back down to Bennu. Some would escape Bennu's gravity forever. Some would actually orbit Bennu a couple of times before they came back down to the surface. And what's even cooler is that we discovered this by accident. Carl Hergenrother, our resident astronomer, was poring over navigation camera images one weekend. These aren't even taken with a science camera, though we certainly used them for science. He was looking through the navcam images just to find like a cool PR shot to release to the press. And he stumbled into this, which turned out to be one of the biggest discoveries from Bennu. All of this stuff is amazingly cool, but in the end, all of it had to lead toward a sampling site. This is the global base map again, and you can see some of the features we talked about, Gargoyle and Ben and the rock. You also see 4 squares. Those were our 4 top candidate sample sites. That list started with a bunch. We all sort of made our own recommendations based on going over this map. That got whittled down further and further to the top 4, and then whittled down even a little bit more to the top 2. The backup site I mentioned earlier is called Osprey. It's sitting there on the equator right next to the Gargoyle, and it's in the lower left of the 2x2 on the right. That's this equatorial crater. But the primary sampling site, and where we ended up going, is called Nightingale. That's in the northwestern corner of Bennu. It's at the top left of the 2x2 on the right. Nightingale sits in a crater called Hoikioi crater that's very dark, pretty big, looked like it had really sort of fine-grained materials in it, perfect for sampling. It had some pretty scary rocks around the periphery, but the spacecraft team was confident that they could get us safely to the center of that crater, and that's exactly what they did. On October 20th, 2020, we sampled from Nightingale. I haven't described this yet, so for those who may not be familiar, the sampling device on OSIRIS-REx is called the TAG-SAM. It's a big disk, kind of about this big if you can see the camera, and it's at the end of a long arm. The idea is, as we descend to the surface, that disk presses into the surface, nitrogen gas fires, kicks up a bunch of rocks that get collected by that device, and then we're just going to bounce off and fire our thrusters and back away. In this video, you can see SAMCAM images on the left, NavCam images on the right, a map in the middle, and when we contact, we saw a lot. It looks like an explosion of material. We're immediately enveloped in this cloud of dust that's shadowing us from the sun. pieces of Bennu are flying everywhere. You can see, especially on the right in the navcam image, stuff is just going everywhere. And this is good news. This means we're mobilizing a ton of material, a lot of which we know is going to get captured in that sampling device. So that all kind of went how we hoped it would. The little bit of surprise that was part of this story is that, like I said, the expectation was that the sampling device would come down to the surface, touch the surface. The arm it's on is kind of like a pogo stick, so it would compress a little bit and bounce off, and then we would fire our thrusters and back up. Well, we didn't bounce. OSIRIS-REx didn't stop when it hit the surface. It kept going. It ended up, the tag SAM, descending almost a half a meter below the nominal surface of Bennu. People liken this to the ball pit at McDonald's. If you were to press your hand against the ball pit, it wouldn't stop on the surface. It would just kind of go into it. That's basically what happened on Bennu. The reason we turned around is because the spacecraft automatically turned on its thrusters after the designated amount of time and backed us away. So it was really exciting, really interesting, and actually probably made the sample better, because that means we didn't stop at the surface. We're not only sampling rocks that are on the surface of Bennu, but we have the opportunity to sample rocks that are beneath the surface of Bennu, which is an even cooler sample to bring home. So now we're excited. We want to see how much stuff did we collect? Did we get enough? Can we store this? And so a couple days later, we took pictures, once we're back safely in orbit around Bennu, of the tag SAM. And we see Bennu stuff. In fact, we see so much Bennu stuff that some of it is leaking out of the tag SAM and back into space. If you zoom in on one of these images, there's on the bottom of the tag SAM, there's a mylar flap that's sort of in the shadows there. And that mylar flap is open during the sampling, but flaps closed to keep the sample safe inside afterward. Well, it turns out that some rocks got trapped in between the mylar flap and the rest of the tag SAM, leaving a gap. And that gap allowed material to leak back out. Every time we moved the tag SAM, for instance, to take a picture, some of that material got jostled around on the inside and some of it leaked out. So now we're a little bit panicked. We're saying we see that stuff is actively leaving. This precious sample that we tried so hard to get is actively leaving. We need to store this as quickly as possible, safely as possible. And so a couple days after that, we stored the tag SAM in the sample return capsule, that white cone that we saw earlier. This is a video or series of images acquired by STOCAM of the arm first placing the tag SAM into the sample return capsule. Then we sort of tug on it to make sure that it's nice and secure. And then we close up the top of that white dome and keep our sample safe for the next 3 years before it returned to Earth just a month ago. However, before we left Bennu, we had one more thing to do, and that was to look at what we did while we were there. Our sampling changed the surface of Bennu, and we wanted to measure how. These plots are very busy. You don't need to see all the detail, but the one on the left is telling you that we made that surface darker and redder than it used to be. Remember, dark things tended to be red on Bennu, and now we've made this surface both darker and redder. That's interesting. The ones on the right tell us that we made Hoikoi crater, the crater that the sampling site was in, deeper because of not only pressing into it with the tag SAM, but when our thrusters fired, it dug channels into the surface of Bennu. So we had this measurable from orbit impact on this planetary body with this spacecraft that we sent up, in 2016. It's pretty cool. But inevitably, it was time to leave Bennu. And on May 10th in 2021, OSIRIS-REx started its 2-year journey home. That journey ended just about a month ago. On September 24th, early in the morning, as the spacecraft approached Earth, it released the sample return capsule. That white dome separated from the rest of the spacecraft, and then the spacecraft diverted and went into an orbit around the sun. Amazingly, we actually have pictures from that release. These are a series of images acquired by our navigation camera. And you can see, hopefully over the internet, that is the sample return capsule leaving from the top right corner of the view and going down toward its target, the Earth. You can also actually see the Earth. If you look on the left side of the screen, that crescent that's just barely peeking into the field of view, that is the Earth. illuminated by the sun. The sun is also just outside of the field of view. That's the bright light coming in from the top. And then all this stuff that's everywhere, we don't know for sure what that is, but it's possible that that is Bennu stuff. That could be Bennu dust that was on or around the sample return capsule that got freed when the sample return capsule was released. I love this video. It's so cool and moody and kind of looks like old school sci-fi, but it's very real.
Looking at looking at this image here, it seems like the Earth is, you know, like you released it a fair piece away from the Earth, or is it just the distortion at the edge of the camera?
Nope. That's absolutely right. When we released the capsule, we needed time for the spacecraft to make sure it didn't follow the capsule toward the Earth, so it was released pretty early. It took 4 hours, in fact, for the sample return capsule to descend from this point until it hit the Earth's atmosphere, and that is actually the next time we saw it. This is the first video we had during the sample return event when the sample return capsule was screaming through the atmosphere at 24,000 miles per hour, and it was just this bright white glow. This was the beginning of a pretty stressful 5 minutes of my life and everyone on OSIRIS-REx's life. This is what we expected to see, to be clear. It was just going to be a white dot. The sample return capsule was using the atmosphere, the friction of the atmosphere, to slow down from that 24,000 miles an hour. So it's this bright light in the sky, but we just had to watch that for 5 minutes, waiting for the next big moment. And I won't make you relive that with me in real time, but 5 minutes after that, after we first saw it, this is the moment we were waiting for. The moment that's going to come in just at the top of the field of view, the parachute. This is when we could all breathe a big sigh of relief. The sample return capsule was back. It was descending. It was the right side up. It was slowly falling back toward the Earth on its parachute, just as designed, aiming for exactly where we thought it would land. This was a big relief. And now the next 5 minutes before it actually landed were a lot chiller, but we were still pretty anxious, of course, to see it when it landed. And boy, did it land. This is the view of the sample return capsule after it landed in the Utah desert. The sample return location was actually at a military testing range in the middle of the Utah desert. So, there's nothing around. And it just kind of gracefully, peacefully descended down and stood there waiting for us. It didn't land in a puddle. It had rained a couple days before. It didn't get dragged through a tree. It didn't, there's not a big scar on the ground where it dragged across the ground while it was attached to the parachute. It's just sitting there looking at us. It's the definition of a picture-perfect landing. It was absolutely amazing to see. This launched a flurry of activity. Folks jumped into the helicopter to go out to the landing site. The first person on the scene was actually in charge of safety. This is a military testing range, so there was the possibility that there would be some sort of unexploded ordnance out there. So his job was to survey the scene, make sure everything was safe. The second folks out were the environmental analysis people. We wanted to document exactly what the conditions were where the sample return capsule landed. We needed to take samples of the dirt, samples of the air. If it had gone through a tree, the tree. If it had landed in water, the water. We needed to know exactly where it landed so that if we saw any contamination in or on the sample return capsule, we could connect that to where it landed and we could know that's where it came from. But after that, we got to the good stuff where they were able to bag up the sample return capsule, attach it on a long 100-foot line from a helicopter, fly that to a temporary clean room that was set up at the testing range. There they were able to make sure that the sample was safe, put it on something called a nitrogen purge, make sure it was all bagged up and ready for its transport to Johnson Space Center. Just the next day, 24 hours later, it headed to the Johnson Space Center and the clean room there, which is where it has lived since then. And that, of course, brings us to the really exciting stuff where we get to see inside. This view on the left is the transfer container, the container that holds the tag SAM in it. You can see the tag SAM there in the middle that was used to transport the tag SAM between the glove boxes and into the clean rooms. And already you see basically Bennu everywhere. All of these black smudges on the lid and all around the periphery, those are probably Bennu dust. And definitely this ring of stuff along the base plate that you see a zoom of on the right, that is definitely Bennu stuff. That's Bennu dirt. It's cool that it's in this pattern where this sort of circular pattern. We think that was because, as I just said, one of the first things they do to this transfer container is to put it on a nitrogen purge. That means that they're flowing nitrogen gas, pure nitrogen gas, into that canister. That is to prevent anything else from flowing in there. We don't want that canister to be contaminated by the Earth's atmosphere or by people breathing. We want this pure nitrogen source so we know that nothing else is getting on the sample. So probably what happened was the first time that nitrogen gas sort of puffed into this chamber, it pushed all of this sample that was maybe randomly distributed around to the perimeter where that lid used to come down. It pushed it all out to the edge, giving us this sort of nice little circle pattern, which also made it kind of easy to scoop up some of that and bring that to our quick look team. 3 days after the sample return capsule came down, we already had pieces of Bennu with our scientists in our instruments at the Johnson Space Center doing what we call our quick look analysis, our very first sneak preview about what Bennu has in store for us. We haven't looked inside the sampling device yet. We haven't seen the real treasure, but this is our quick little sneak peek into what Bennu is going to show us. And that sneak peek is pretty cool. These are images from a scanning electron microscope. So this is like a microscope you're used to, but it uses electrons instead of light. And that means it can see very small things. If you look at the scale bars in the bottom, you see 2.5 microns, 5 microns, 10 microns. A micron is 1,000th of a millimeter. And 10 microns, the largest scale bar we see here, is basically the width of like a red blood cell in your body. The hairs on your head have a diameter of tens or hundreds of microns. So this is really, really tiny. And these are cool not just because we can look at really, really tiny things, but what these tiny things tell us. In the top left, we see, believe it or not, it's hard to interpret, water-bearing clay fibers, clay minerals. These are those minerals that have water locked up inside of their crystalline structure. This is what we saw in spectra from orbit at Bennu, and here we have confirmation that we have these water-bearing minerals. This is important, not just because it's neat, but because we think that the way water was first seeded on the Earth might have been by asteroids like Bennu, not Bennu obviously, transporting water around the solar system. It could be that how water got to the Earth was one of these inner planetary travelers landing on the Earth. In the top right, we see something called a sulfide. Sulfides are very important, not only for planetary formation, but for the building blocks of life. So again, this is something that might be transported around the solar system. In the bottom, we see 2 iron oxides. These are also called magnetites. The bottom left one has this cool, it's called a framboidal structure. It looks kind of like a raspberry, all these facets. We see these all over the place of different scales. It's really interesting. In the bottom right, we see a more sort of plate-like structure. And those actually, it turns out, are also important for the building blocks of life. So we're seeing immediately really important stuff, the stuff that we hoped to see in Bennu, and it's just kind of confirming that we really did choose the right target. This is the stuff we wanted to see. We have other ways of looking at it, including X-ray computed tomography. So this is very much like a CT scan that you get at the doctor's office, but here we're doing it with X-rays on these very small, this is only a millimeter across, very small objects. And from that, we can build up not only the shape of the structure of the rock, but we can also look inside of that rock. All of these red dots that you're seeing are those sulfides that we just saw in the SEM image. Those are scattered throughout this rock, but we see those without ever having to open up the rock. So now we haven't disturbed them yet, and now we can see, oh, well, maybe I really want to look at sulfides. Now I kind of know how I want to segment this rock to get in there and see that thing I'm interested in studying. So right away, like I said, within a few days of sample return, we're getting these super cool results. And while that is all happening, the curation team at Johnson Space Center is proceeding down their sort of very well thought out, methodical plan for how to access the sample inside of the tag SAM, inside of the sampling device. But before we even have to do that, there's actually a bunch of it just sitting on top. This is the underside of the tag SAM, but it's on its head now, so this is sort of the top as we're looking at it. That thing in the middle is this metal cone, and the gray circle around it is that mylar flap that we were talking about earlier, the one that opens during sampling and then is supposed to close after. Well, the supposed to part, you can see in the box in the upper left, the box marked B, and in the upper left of the 2x2 on the right, that is one of the culprits, one of the tricksters that managed to keep the mylar flap from entirely closing. It and its friends around it are what made that gap that allowed material to escape just after sampling. So it's on our bad list a little bit, but it's also a really cool rock. It's like a centimeter across and a beautiful example of what Bennu has for us. In the top right, you can see a zoom on really, really small particles. These are all like smaller than a millimeter. But even for these really small particles, you see all this diversity. You see the bright things and dark things. In the bottom left, the box marked D, we see one of these dark, rough rocks. We call them hummocky, that seem like they're really fragile. Like if you were to put too much pressure on it, it might just crumble. And in the bottom right, we see a pair of rocks that just happen to be next to each other that might be examples of the dark and light rocks on Bennu. We see the one on the left is a little bit darker than the one on the right. Maybe these are an example of the two populations that we thought might exist from our orbital data. So right away, we're seeing all kinds of cool stuff. There are, I can't remember, like a few grams worth of material just sitting on the top of the tag SAM that we could immediately see without even going digging. And then we get to our first roadblock. So as you may have seen in the news, if you keep up with this stuff, the curation team at Johnson Space Center has a very methodical, careful plan for how to access this sample. This is some precious stuff, right? There's been a tremendous amount of time and people and money that has gone into this collection. We don't want to do anything that would risk it. So there's a very slow process for how we get inside. And that includes sort of disassembling it step by step. That also includes removing something like 35 screws from the tag SAM in order to access the interior. Unfortunately, 2 of those screws turn out to be very stubborn. For reasons that we can't know yet, maybe they just the materials do this thing called cold welding, which can happen with metals, and particularly can happen in space where the metals just sort of bind up on each other. But for whatever reason, with the tools we have available, it was tricky to get them open. And we do have a limited selection of tools because, again, we want to be very careful about this. We can't just come out the tag SAM with a hammer and a hacksaw. We want to be very thoughtful about maintaining the pristinity of this sample. That means not only a limited type of tools, but limited materials of tools. We don't want to be looking at a rock from Bennu and wonder if that rock is Bennu or a bit of a screwdriver. So we have to use very specific materials, clearly defined, that make up our tools that allow us to access this stuff. So we had to take a pause here. We had to say, okay, these screws are being stubborn. We don't want to rush anything. We're not in a rush here. We have plenty of time. We do not want to risk this sample. So what can we do at this point if we can't get these screws open immediately? And the first obvious answer is there's all of this material just sitting there. We can easily scoop that up without opening anything. So we did that. And as the curation team was doing that, they saw a lot of material inside the tag SAM. Because remember, again, this mylar flap presses down, right? So as they were scooping stuff up, they were seeing the stuff behind it, inside the tag SAM. And they realized pretty quickly that they could access it. If they just pressed down a little bit on the mylar flap after they got rid of all this stuff on the top, safely containerized and put away, they could reach into the tag SAM with tweezers or with a scoop and get some of the material that's inside the tag SAM. So there was a lot of meetings, and we decided that that was the way forward, that we would get all of the sample out of the tag SAM that we could easily and safely get. We're not going to be digging around. We're not going to be scraping all the corners. We don't want to endanger this precious sample. But the stuff that's just there and easily accessible, we might as well get. And so that's what we did. Now, this is the sad part of the presentation. I cannot show you that sample. This is an image of me and some of my colleagues in the clean room at Johnson Space Center. And what's behind that redacted sign is the sample inside of the glove box in the OSIRIS-REx clean room. Unfortunately, I can't show you that sample. As you might imagine, there are lots of rules about how this sort of stuff is released, and we just got access to this stuff this week. I was at Johnson Space Center earlier this week to do this. That's when this picture was taken, to look at this sample. So unfortunately, I don't get to be the worldwide release of the images of the sample from inside the TAGSAM. So I can't show you what it looks like yet.
But you've done an excellent tease for when it is finally. We're all going to be sitting on the edge of our seat here.
Great. But I can tell you that we pulled more than 70 grams of material from on, around, and mostly inside of the TAGSAM. Now, for those who don't know, the requirement for the OSIRIS-REx mission was 60 grams. In order for our mission to be considered a success, we needed to bring back 60 grams of material, 60 grams of Bennu, to the Earth. Just by the stuff that was on, around, and mostly by reaching through that mylar flap to pull out the rocks and the dust that we could get to, we have over 70 grams, which is amazing, because we know there's more in there. You don't know how much because we can't see past that mylar flap, but we know there's more. But even if that was it, and it's not, we already have met our requirements for the mission, which means, well, it really means two things. One, the curation team can take the time they need. They can figure out, they still want to get into TAGSAM. We still want to get to the rest of that material. They can pause and say, and design a new procedure and say, how are we going to get to that material in a safe way and not feel rushed? Not that we would have rushed them, but now, you know, the pressure's off. They have time to consider how to do that safely, to practice it. We have sort of backup TAGSAMs that we can practice on, so they can really know that they're doing the right thing to get to that sample. Simultaneously, the science team, the dozens of scientists across the world, can get started on sample analysis. This is more than we needed to have in order to do everything we wanted to do with our sample analysis plan. So that plan has started. That's why I was there earlier this week to take pictures with a camera that me and my colleagues built in order to take our first sort of evaluation of these 70 grams. That evaluation leads to who gets what. Dozens of scientists across the world want some pieces of Bennu. We have a bunch of defined allocations for who gets what and how much. But some people want a big rock, some people want dust, some people want something that's got this texture or that texture. So these initial images are how we triage all of those requests. And that is going to start happening maybe next week, the week after, where people will start making these requests for what they want, and some of those samples will be sent out to all these laboratories and all these instruments around the world to start doing the real science. The whole reason we brought this sample back to Earth was so that all of these instruments, things that we could never put onto a spacecraft, could be applied to the sample and really start to tell us what Bennu is all about. So I'm sorry that I can't show you the real thing. I really wish that I could. But like I said, this is brand new. They just put out the press release about the 70 grams a couple days ago, or a few days ago. I have no doubt that very soon they will be releasing images in more detail about it. Unfortunately, that can't be here, but I'm confident it will be pretty soon. So this kicks off the next 2 years of OSIRIS-REx, the sample analysis portion. But you may remember the end beyond part at the very beginning and the title of the talk. That is not the end of the spacecraft story. I had just said that after we after we let go of the sample return capsule to Earth, the spacecraft diverted into an orbit around the sun. This turns out to be a very deep Earth-crossing orbit. It has a perihelion. That means the closest point to the sun of 0.5 AU. So that's as half the distance to the sun as the Earth is away from it. So the OSIRIS-REx is now headed to an orbit to, in January, cross this perihelion point. That, combined with the fact that we had excellent performance at Bennu, not only getting to and from Bennu, but operations at Bennu, the spacecraft team did a fantastic job, means that we still have fuel in the tank. Enough fuel to get to a different target. So we are going to arrange 6 more of these perihelions, well, 6 counting this first one, where we get very close to the sun. 3 more EGAs, Earth gravity assists, 3 more times where we're going to use Earth's gravity to boost us in the right direction. And that's going to put us on approach to an asteroid called Apophis. This is an image of Apophis on the right. This is not a real image. This is as real as that expectation image of Bennu I showed you earlier. It's just the general shape we have from radar. You may not have heard of Apophis yet, but I promise you, you will hear about it in 2029. Apophis is a little bit smaller than Bennu, 200 or 300 meters across, kind of shaped like Eta Cavo we saw earlier. But the reason it's important is because it's going to come very close to the Earth. It's not going to hit the Earth, we know that, but it will become very close. It will come within 1/10 of the distance to the moon. So the moon is this far away, 10 times smaller than that is how close Apophis will come to the Earth. It will come so close that people in Europe and Africa will be able to see it with their naked eye at night, which is not a thing you can ever say about asteroids. It's going to be a huge worldwide scientific event. Telescopes across the world are going to be studying Apophis as it comes close. Other institutions might send up spacecraft to look at Apophis. And just after Apophis's close approach, our spacecraft, will catch up to it in order to study it. But at that point, we won't be a Regolith explorer. So we're not going to be OSIRIS-REx anymore. Instead, we will be OSIRIS-APEX, for Apophis Explorer. At Apophis, we will do all of the same global science we did at Bennu, all of the same spectral studies, looking for mass shedding, making maps of the surface. The only thing we can't do is a sample. We've already used our one sampling device. But that actually is the opportunity for a new experiment. As we saw at Bennu, the sampling event itself changed the surface of Bennu. So what if we did that on purpose? After we've done all of our global studies, all of our spectroscopic studies, we will purposely get very close to the surface and fire our thrusters and back away, and then re-observe that surface and see how we changed it. See not only the effect that we had, but presumably that effect will reveal the subsurface of Apophis, which will give us a whole new thing to study. It's going to be pretty cool. I hope you're excited for 2029. I certainly am. But with that, I'm going to say thank you, and I would be more than happy to answer any questions.
Oh, excellent. Excellent, excellent. Well, I know we've got at least one question from the chat, but do I have any questions here in our room right now? All right, well, let's go to the chat. Let's see, their handle is FW-STVC, and they ask, does this hydration mean there is definitely some water on Bennu?
So it's a great question, and one that comes up often. I should have probably expected it. So this does not mean that there is liquid water on Bennu. What it means is that water molecules are locked up into the crystal structure of the minerals on Bennu. That means that at some point in the far distant past, maybe on Bennu's parent body, probably on Bennu's parent body, there was water that interacted with those minerals in order to get it locked up, but that water does not exist in a liquid form or any sort of water form that you would expect on Bennu currently.
Interesting, all right. We do have another question out of the chat from Fred. I said, first of all, very interesting presentation. Where and when in our sky is Bennu? Is there a website that tracks its location?
So there is absolutely a website. There's a cool JPL website. You may be familiar with them from California, where they track the ephemeris of a lot of asteroids and other planetary bodies that we know in the solar system. So you could totally go Google Bennu's orbit and find out exactly where it is right now. Unfortunately, Bennu is much too small for us to see with our naked eye. In fact, it's much too small for most telescopes to see. It's only when Bennu happens to get close to the Earth that we're able to do any observations of it. So it's never a thing you're going to be able to see from your backyard, but you can absolutely find where it is literally right now on the internet.
Very cool, very cool. I noticed in one of your way earlier slides when you had that sort of large projection map of Bennu, there was a fairly substantial, fairly round depression, or what would appear to be. is that one of the craters that you were talking about?
Let's see. Let me see if I can find what you're talking about.
Let's see.
Let's get through all these. There, here we go.
Yes. Oh, just back one. Lower right-hand corner.
Yep, yep.
That seems like
yeah. So that. Oh, it's.
No, so
is it caught up?
Okay. Did we lose you?
I'm still here. Did the video catch up?
Yeah, no, there we are. There we are. Yeah.
Yeah, so in the lower right corner, yes, absolutely. That is one of the largest sort of crater features on Bennu. In fact, that crater is the location of one of our top 4 sampling sites. The candidate sampling site called Sandpiper was inside of that crater. That's actually a really interesting one because not only can you see that crater, you can see the results of the ejecta, what was ejected off of the surface during whatever impact from that crater. It's hard to see in this data, but there are other visualizations of the surface where you can see sort of the pattern of material that ejected off of that crater into the north in sort of this very cool pattern. You can see it in multiple forms of data from OSIRIS-REx.
Sure, yeah, you can. It's sort of like a almost like a V pattern going to the north.
Yeah, it's sort of this lighter, smoother area because it's covered in whatever blew out of the crater after that impact.
Right, very cool, very cool. I'm going to go back to the in-person audience. Any last questions? And we'll go to the chat then. All right. Well, again, you've done an outstanding job of answering the questions that we probably already had, and I really want to thank you. I know that especially at this point of a mission where literally every day you're discovering something new that you guys are, you and your colleagues are all doing, phenomenal work. To be able to have you spend some of your time with us today, and those people watching on the live stream, we really very much appreciate it, and we wish you and the colleagues, the best of luck getting into that final inner chamber, and look forward to hearing more about that. We will, as you have some news to share, we've actually done some sort of watch parties, and we actually did a watch party for the actual sample, tagging on our YouTube channel, and so we'll continue to do that. So.
Yeah, it's a very busy time for us. Obviously, it's a very exciting time, but this is not just for the scientists, right? First of all, this is funded by the U.S. taxpayers, so everyone owns a piece of this. But more importantly, it's the fact that all of you all are interested is what keeps this work going. So we are always more than happy to come and talk to folks about all the cool stuff that's coming out.
Well, again, really do appreciate your time. And what I will tell the people here is that I believe we still have some clear skies. Saturn is up, the moon is up, Jupiter is up. So we invite you to come out and we actually have a nice moon filter on the scope looking at the moon, so you won't get quite as blind. Being practically, I think tomorrow is a full moon. Anyway, so Dr. Golish, thanks you again. It was just outstanding.
Thank you so much.
Have a good evening and a good weekend.
You too.